Thanks for stopping by the channel today. My name's Jason. I'm KC5HWB. This is the extra class. This is the final class in the 3 classes of amateur radio licensing that exist in the United States today. Some of my most popular videos on this channel have been the technician class and the general class, which is class 1 and class 2, or level 1 and level 2, if you will. This is level 3. This is the final level. This is the top license you can get. And I want to thank the North Richland Hills Amateur Radio Club for allowing me to record this Zoom class they did at the end of 2020, beginning of 2021. It was about 8 6 to 7 hour sessions, so you're in for a wild ride today. Go through them as many times as you want to. Fast forward, stop, pause, rewind, whatever you want to do. Play them over and over again. This is good information for those of you who are currently a general and wanting to upgrade to amateur extra. Thank you to the North Richland Hills Amateur Radio Club. Their website will be linked in the description of the video below. And I hope you enjoy the video series.
This first section is found in your books on pages 75 to 80. And it's on the visuals and video modes. And we'll get right into it. I was impressed even as a novice in 1959 that hams could send television pictures. My Elmer had a Type 15, Model 15 teletype, so I had a little experience with TTY early. When slow scan television was inspired by the moon landing technology, I tuned the Tweety birds on 14230. Was amazed that those were pictures, though I could not decode them at the time. And it first started out, you used a high persistence oscilloscope tube. And it took 8 seconds to send that fuzzy green picture that I saw in the magazines. And the thing that amazed me was that you could send it via a single sideband transmitter on HF. This slide that you see here is a screenshot of a signal that I actually received from a Canadian station. This is really a very good picture, except for the interference that you see when it got to the DE part. And I was kind of disappointed when I went back in to find pictures. This was the best one that I had in the slow scan software. And I did not have a single thing of a response to a CQ. They were all the slides, even the worst of them were CQs. And apparently that morning, when I did that last spring, the band wasn't doing so well, and there was not very much communication. I remember it as a day when there were 5 or 6 QSOs that I saw. But with that amazement, we're going to deal with the technology a little bit. And the first question that we want to deal with, you'll note out of the question pool at the top, there's a number. It's extra, section 1, section A, subsection A, question 12. And then the little thing in the bracket is actually the answer. But that first question is, what special operating frequency restrictions are imposed on slow scan television transmissions? And A is not correct. They are not allowed on all amateur frequencies. They are not restricted to that list of frequencies. In fact, none of those frequencies is a standard slow scan television frequency. And they are permitted above 54 megahertz. And that means that the answer to that question is they are permitted in the phone band segments. The second question is, how is the color information sent in analog slow scan television? There are lots of ways that can be done, and there are several different software generations of slow scan pictures. But basically, in all analog imaging things, the thing is to scan a line with the intensity of the signal. And in slow scan television, those lines are sent sequentially. And I don't know whether it's red, green, or blue, or which sequence the color lines are sent. But in color slow scan television, which takes about 30 seconds for the picture to be sent, you get those 3 lines sent, and then the computer software combines them. The other answers in this particular questions are bogus. There's no subcarrier with slow scan television. There's just that one 3 kilohertz signal with a black line, and it's frequency modulated so that the darker is and the blanked out retrace synchronization pulses are on one frequency, and the brightness, luminance stuff is on another. So the technology does not support any kind of a subcarrier. There's no color burst as you might have in fast scan television. And the technology is just a line at a time. There's no amplitude versus frequency modulated stuff in it. So the answer is still that the color lines are sent sequentially. On the exam, depending on the computer that generates it and the random nature of it, these answers may not be in the same order. So don't try to remember the answer to E2B04, which that number won't be there, but how is the color information sent? The answer might, the color lines sent sequentially might be answer D in some or C or B in some of the generations of the test. What aspect of the analog slow scan television signals encodes the brightness of the picture? And since that luminant signal is frequency modulated on it, it's the tone frequency that generates the brightness of the picture. Does anybody know if the highest frequency in that signal is the brightest, or the lowest frequency in that sequence is the brightest? Does anybody know?
Well, the book says the highest frequency is the brightest.
Okay. Yeah, I'm not looking at the book, but that is true. The darker, if you look at the waveform, the audio waveform on an oscilloscope, The synchronization and the black are, if I remember correctly, something like 1200 hertz. And the white would be up about 2500 hertz in that demodulated audio signal. What signals what signals the SST receiving to begin a new picture line? And that synchronization is the tone frequency, and it's the marker frequency at the bottom end of the at the I'm getting some echo at the bottom end.
Can we ask that those that are talking mute their audio, please?
Yeah, it looks like everybody has. The sync signal is the bottom frequency in the thing, and so the answer is specific tone frequencies do the synchronizing. It has it's not sync based just simply on time, although the length of the line is a very specific time, and tone amplitudes. It really is basically an FM type signal. So the answer is the A at the top.
I got a question that in the other question, the previous question.
Okay.
I use a lot of the SSTV, especially in 14.230. I leave it all night long as a repeater in my home station. So the question, the specific tone frequency, that's the beginning of the SSTV, the two-tone type deal that you hear, and then start the actual picture. That's when they send the signal to determine what is the mode that you're sending.
There they go again. John Dale and I are both a part of that. And I apologize, gentlemen. I don't know how to disable that at this point. Come back with your question again. I just got my mind blown out of the water.
I use a lot of I use SSTV a lot,
Awesome.
and I leave it. Yeah, I got my station set up as a repeater for SSTV. So every time you send a picture out, you have a distinctive two-sound initial burst before start. I wonder if that's the specific tone frequency they're sending out to determine the mode they're sending and for the other end to receive it.
Yes.
Okay.
It cues the software to the fact that you're starting the picture. If you have been receiving something and somebody comes on and gives a second signal that's a little stronger, the second signal will dominate and restart the frame. And
Gotcha.
the way it does that is that burst of data at the top, which defines or tells the software what mode of slow scan television is going. Thank you for that question. And this question really deals with that. What is the function of the vertical interval sequencing code sent as part of the SSTV transmission? Answer is B, which is to identify the SSTV mode. And what you're talking about is that VIS code that's being sent at the first of the frame. And there is no color burst oscillator because you're sending 3 different images in order to get the color, a line at a time. The VIS code is not a synchronization code, it's a mode identification code that the software recognizes. You might get tricked into that if you think of what happens if you get a stronger signal that steps on there and it restarts the frame, but the vertical stuff goes line by line and it's synchronized really by the end of the line signals. And it has nothing to do with the call sign of the station. In the early days of SSTV, in order to operate legally, at the end of every SSTV transmission, you had to identify your call with a burst of Morse code that identified your station. But that's not the VIS signal. The VIS signal is really to identify the SSTV mode. Here's one that I had to do a little research on before I could deal with it, because I was not aware of this mode of operation being used in ham radio. And the question is, what hardware other than an SSB receiver and a suitable computer is needed to decode slow scan television using the digital radio mondial? And this is not the DMR, this is DRM. DMR is the digital mode for audio in VHF transceivers. This particular mode, as you look down, I looked it up and attributed to Wikipedia. It was actually an engineering company that posted this, so I've got to go back and reattribute it correctly. But it's a digital commercial broadcasting mode used in shortwave broadcasting, and it's supposed to deliver an FM comparable sound quality even on shortwave. And it's a digital alternative to shortwave, and it's implemented in the WinDRM adaptation for ham radio. It uses a technology called coded orthogonal frequency division multiplexing, and that intriguing thing of quadrature amplitude modulation, which probably could have an hour lecture, but basically it's a software generated modulation system. And that note had the thing that I've highlighted in yellow with question marks at both ends. DRM is commonly seen with 10 kilohertz bandwidth, which works for shortwave broadcasting, and other bandwidths are used rarely, and that raised all kinds of red flags for me, because in ham radio the magic number for bandwidth in the HF bands in the phone bands is 3 kilohertz. So what's the answer to the question? What hardware other than an SSB receiver and suitable computer software is needed to decode? And the answer is there's no other hardware needed. The trick is in feeding the audio into the SSTV. And if you've operated any of the digital modes or operated slow scan television, you know that because you put the audio out of your receiver into the computer input and load the software and away you go. So there's no special IF converter needed. There's no special front end limiter needed. There's no special notch filter to remove sync pulses or anything like that. It's just receiver and computer. And that's it. The next question is, which of the following is an acceptable bandwidth for digital radio Mondale based voice or slow scan television digital transmissions made on the HF amateur bands? And you got the question up here that says 10 kilohertz is the standard. And down here you get a whole range of things. Just remember the magic number is 3 kilohertz because that's the bandwidth that is good amateur practice. So the 10, 15, and 20 kilohertz, while technically possible, are not acceptable for voice or slow scan television in ham radio. Okay, we move on to analog high-speed television. In all my years, one of the first questions I asked when I joined the North Richland Hills Amateur Radio Club was, is anybody on fast scan television? And the answer I got back was, well, there was somebody years ago, which didn't help me a bit because I really would like to be able to receive some analog TV. Analog TV began, is there a question? Got some crosstalk or something. Analog TV began, I guess I'm getting a feedback from my audio. It began with a technology that used a disc in front of a photo tube. And the first television that was sent when Herbert Hoover was the Secretary of Commerce, and the signal was sent from, Baltimore up in the Maryland, D.C. area. That camera was a flying spot scanner, which is on display at the Hoover Library in Iowa, which I found extremely fascinating. The electrical implementation of the receiver was a cathode ray tube, and the early TVs were only 5 inches in diameter, and you had this square thing, so you had a corner. That's why they measure the picture from corner to corner, because that was a 5-inch TV screen. And in the early days, the 30 frames that were used they chose it because that was the frame rate, or was close to the frame rate for motion pictures. And if you did a standard 30 frames, line after line after line per second, it came across with flicker. So they went to a 60 cycle thing, scanning it twice to get the 30 frames per second, and synchronized it to the electrical grid. And it was back in the late 70s when the video recording was implemented, that they got away from the synchronization to the electrical grid. Out of all of that, the NTSC standard for television, it got modified to allow for compatible color using a 3.549 megahertz chroma subcarrier. And you can guess which frequency in the 80 meter band was unusable in many areas, because all the TV sets were radiating a 3.549 megahertz chroma subcarrier. The crystals for that were really cheap, and I had a crystal that I used in my CW transmitter that I bought. It was a chroma subcarrier crystal. Nobody could talk to me because nobody could hear me, because the QRM nearby. And to synchronize the interlace, it takes an odd number of lines, and the 520 lines in the NTSC standard was adopted because it gave approximately the same vertical resolution as the horizontal resolution for the 3 to 4 aspect ratio of the television pictures of the time. We now live in a digital age where digital television does all kinds of different lines. And if I look at my monitor, I can pick lots of different aspect ratios. So with that little background, we'll move into the questions. The first question is, what technique allows commercial analog receivers to be used for fast scan television operations on the 70 centimeter band? And that technique is simple. You tune the TV to the frequency in the 70 centimeter band, and there are 2 channels that are in the TV band that are cable television channels. So all you have to do is have an analog TV receiver and an antenna and a station to transmit to you, and turn that thing on, turn it to the channel, and the standard ham frequencies and the cable TV are close enough that the automatic frequency control in the television set will lock onto the ham signal. So even though the cable TV channel is not identically the ATV frequency, it's close enough most of the time. And I'm still looking for that local ATV station so I can do that.
John.
Yes.
I'll say, yeah, in the Durham, North Carolina area, one of the local clubs, they still have the actual repeater set up for fast TV. And it's very interesting. And one of the transceivers at one point was really expensive when the club started, because you had to actually find the local TV transceivers, all ones that nobody wanted. But now you actually get some like for $300 and connect to any camera system.
Ah, that's good to know. One of the things that I find exciting is that the audio for ATV is not necessarily the NTSC standard at 4.5 megahertz above the TV carrier. But very often the audio will be done using a local repeater on 2 meters. And that's a good way to get people interested in getting an old analog TV and getting it tuned to ATV and getting interest going in the community. So the technique is really getting a receiver and getting it hooked to an antenna. It has nothing to do with satellite dishes, and you better stay off of the abandoned TV channel 2, because that's 54 to my wife has got a problem with the printer. It's unplugged. Sorry. So fast scan television is not going to be modulated with a computer sound card, obviously. So the answer to the question, what technique is transmit on the channels that are compatible with the cable TV on the analog receivers? How many times per second is a new frame transmitted in a fast scan NTSC television system? And at 30 frames per second, that's the answer. And you don't get confused with the others. But think of it as the frame rate for a motion picture camera, and that's between 25 and 30 frames per second. So the fast scan television, it's 30. How many horizontal lines make up fast scan NTSC television frame? And the answer to that is the 525. It's not the frame rate, and it's not the AC line rate, and it's not the 1080, which is high def digital resolution. It's 525 lines. The question is, how is an interlaced scanning pattern generated in a fast scan NTSC television system? And the answer is that you're really interlacing the things by scanning odd numbered lines in one field and even numbered lines in the next. There's none of this 2 fields simultaneously. It's not scanning top to bottom. It's not scanning lines from left to right in one field and right to left in the other. They all go from left to right. It's the odd number in one field and the even numbers in the next. The what is the name of the signal component that carries the color information in an NTSC video? And it's the chroma, which is Greek word for color. It's not, luminance is the brightness information. Hue is a characteristic of color, but it's the chroma that's there, and spectral intensity is just a stray answer somebody threw in to make a fourth question. I'm going to have some questions coming up about vestigial sideband. This is a diagram that doesn't quite show it the way I would like to show it, but basically the vestigial sideband is when you have the carrier frequency, you've got signal above that frequency and you've got signal below that frequency, as in AM, except that it's filtered in such a way that you get only a part of the envelope below the carrier frequency, and then all of that information is repeated above the carrier frequency. And then in a video, NTSC video signal, you've got an audio carrier, and it's FM, and it's not 4 megahertz, it's 4.5 megahertz above the carrier. So the graph is off, the chart is off there, misinformation. But that's the frequency spectrum of a TV signal. A little bit over here on the lower part, and because it's duplicate information on both sides, it supplements that lower part of the TV signal when it's demodulated. But all of the video information is carried in this segment. And a NTSC TV signal was allocated 6 megahertz of frequency. The current digital is allocated 6 megahertz, but you can have a lot of pictures in that 6 megahertz because of the signal processing. The chroma picture subcarrier, 3.549 megahertz. The chroma information is phase modulated on that color burst carrier. And it turns out that it has very little effect on the actual video signal, even though it's transmitted simultaneously within the passband of that video. So we get into questions. What is digital sideband modulation? And the answer is A, amplitude modulation in which one complete sideband and a portion of the other sideband is transmitted. And it's not sideband's inverted. It's not narrowband FM modulation. It has to do with this below the carrier portion. And if you modulated it just pure simple AM with no filtering at all, it would be symmetric. And what you had on the right-hand side would be on the left-hand side. But it's vestigial. It's just the remains or the lower frequency portion of that stuff. Which of the following describes the use of vestigial sideband on analog fast scan TV transmissions? It does not carry the audio. It does not carry the chroma. The audio is 4.5 megahertz up. The chroma is 3.549 megahertz up. The vestigial is that duplication of the lower sideband of the TV picture, which is C. Vestigial sideband reduces the bandwidth because you're not sending the whole thing. You're just sending it's not single sideband, but it's what's left after you filter off the high frequency stuff. And doing that allows for simple video detecting circuitry. Because the carrier is there, you can use just an envelope demodulator if you wanted to. And vestigial sideband cuts off the high frequency stuff, so that answer makes no sense at all. So the answer is C. And that is the end of this thing on visuals and video modes.
In case anybody hadn't guessed, I'm sitting at my computer end of the ham shack. This is where I sit and work while I work from home, which is most days nowadays. The other end down there is the radio end. That's where the antennas come in, the radios sit. So I kind of keep it separate that way. However, off to my left is the window where I've got a couple of antenna wires coming in. Like I said, I like to experiment with antennas so they change frequently. This section is Skywaves and Contesting. If you've got the book, page 43. Let's see, I need to share my screen. And there's the file. Okay, Skywaves and Contesting section. Now we're going. And if you want to follow along in your Gordon West book, it's page 43 that we'll get started on. But before we start through the questions, let me put this in presentation mode so it's a full screen for you. And we'll go down through some slides. And hide this so I can see everything. There we go. Now we're going. Okay. Page 43 is where this section starts, but let's talk about this. A lot of this is intended to be review from general and technician license classes, which I've taught both. And also, this is second or third time through teaching the extra class material. And so if I seem to remember some of it, it's because I've been over it before 3 or 4 times. But some of this will be review, and some of it, if you've just received your licenses and license classes, you've seen it recently, or maybe you need a refresher, whatever. But we'll go over several things on each of these slides. This is intended to be the northern hemisphere of the Earth, is what you're looking at, and showing the layers of the ionosphere. Now, obviously, it's not to scale. Consider the scale of this picture. You see down at the bottom of the slide is approximately where the equator is. I got it off that southern end of Western Africa, about where my map showed where it was. It goes right through the Indian Ocean. And across the equator right there, the diameter of the Earth is about 8,000 miles. So I put I'm not a metric thinker in miles and kilometers. In small dimensions, I can think in metric, but the big dimensions don't work so well. So if you see there, it says the top of the F region is about 260 miles, 250 miles maybe. Well, that's really a very shallow shell around the Earth, because the Earth is 8,000 miles across in diameter. So, you know, just stop and consider that. In the past, in in-person classes, I've used my globe and laid a piece of paper on top and said, this paper is about the thickness of the ionosphere in relation to the width of the globe. And the globe was, my globe is like, 12 or 14 inches diameter. So it's a very narrow, thin shell around the Earth. And it is a shell set up in layers. The layers during the day over to the right where the sun is are a bit different than they are at night. And nighttime sky is to the left. And the approximate layers are there. There's no clear boundary between the layers. And that's going to be one characteristic of how the radio waves bounce around between the layers, between the Earth, and propagate through the layers, is that every boundary between each of these regions is a curved mirror for some frequencies. Some frequencies fly right through, some frequencies get absorbed, some frequencies just reflect back off the bottom region, the D or the E, depending on day or night. And we'll go through several things that the curved mirror effect causes. If you've ever seen curved mirrors or been to carnivals or state fairs where there's curved mirrors, they do some really strange things to images. Now consider this, that light is an electromagnetic wave, really of the same characteristic as radio waves. Radio waves are just very much longer wavelength than light. Light's a very short wavelength electromagnetic wave. And every boundary in the atmosphere, all the way from the Earth itself, a few thousand feet where the temperature starts changing, that becomes a boundary, is a curved mirror. And all these ionospheric regions are curved mirrors. So that's where the electromagnetic waves get reflected. There's several things going on here that we need to talk about. The equator's there, and over to the lower right-hand corner shows a propagation path called the transequatorial propagation path. It's a path that hops over the equator to approximately the same distance south of the equator, maximum of about 5,000 miles, and it maximizes in the afternoon. Now, there's keywords in here, and there's some, pardon me, there's a few numbers. There's a few keywords and a few key numbers. The distance in miles, not so much, but this 5,000 maximum for transequatorial is a clue. And in the afternoon, I wouldn't mention it just because that's when I'm the happiest and most want to get on the radio. That's really when it kind of peaks. and clues are answers to questions. So if you pay attention to the clues and all the little details on the drawings, you can remember a lot of the answers. On the nighttime side, there's some more interesting things happening. We have the aurora, which occurs mostly in the E region, which is the first ionized layer up above the Earth. And CW is a really good mode to be working aurora propagation effects. Then at times, especially in August and middle of December, you have meteor showers. Meteor showers will set up a charged linear reflector. What it is, it's a charged stream of electrons. And anytime you have electrons, radio waves bounce off of those. They bounce around electrons and magnetic fields, which we'll get into later. But the meteor shower sets up a stream of electrons. That's that red ray. And yes, they go in straight lines. If you've ever seen a meteor shower, I personally haven't seen a good one. I might have seen a meteor once, but that was it.
Yeah, I saw one August night in Iowa, out in rural Iowa, counting meteors, and the Perseid shower that year, I counted 60 an hour for 3 hours, so 270 meteors. There's a January meteor shower as well. I've never worked meteor scatter on ham radio. I've only just visually observed the meteors. But if you're out in a rural area here in Dallas-Fort Worth or up in New England, around New York and New Jersey, there is no star in the sky and you can't see the meteors. But if you get out in a rural area where there's not light pollution, on any night, there will be 2 or 3 meteors per hour. And I understand the principles, how to work it. You set a schedule with somebody you want to talk to, both aim your beams at the region between you, and alternate transmitting. And the digital modes are specifically designed for that.
Right.
And, when you, the first round you send your call, and the second round you send when you have heard the other person, you get a received and a signal report. And when both of you have done that after 3 hours, you can count the contact, because you've given 2 bits of information that cannot be given except via radio, which is a confirmable contact.
Yes.
Sorry to interrupt. Go ahead.
Well, that's fine. That's good. I'd like to see one of those meteor showers sometime where you get that many. But the Perseids and the ones in December, I forget what they're called, are the good times to try and attempt meteor scatter operation if you're into that, if you'd like to experience it. The frequencies that are usually used are 10 to 2 meters using a mode MSK 144. and all the choices are correct on the meteor scatter question. Lower left-hand corner, sporadic E is, as its name says, sporadic, which can occur any time of day, and the best time of the year is during the summer, around the summer solstice, end of June. So you might want to refer back to this page at some point, and we might do that during the questions. Another presentation that we can look at to view propagation is by ray tracing. This is doing some ray tracing from antennas as the electromagnetic waves bounce off the different ionospheric layers. Now, for the different frequencies are affected by the different layers. The angle of launch from your antenna will affect how the wave propagates around through the atmosphere and through the ionospheric layers. This one doesn't show day or night, but there's several things here. Is that the higher frequencies can travel further before they're being reflected. Lower frequencies launched at lower angles will go farther and have skip zones. You see where it says skip there, middle right, there's no energy from that electromagnetic wave that reaches the earth. So nobody under that skip, under that hop up in the ionosphere can hear that signal. It goes from one antenna to the other. There's a thing called a chordal hop, which is much less lossy because the earth is lossy when the radio waves can bounce off the earth. They can bounce off and have several, like multi-skip. If anybody's ever heard that term or experienced it, there's several hops the radio waves can take, bouncing off the ionosphere and back off the ground and then back through the ionosphere again before it lands on somebody's antenna with a receiver on. Bouncing signals over the ocean is good for that because the ocean is a sheet of salt water. Although it's not a perfect mirror, it still has ripples in it, lots of ripples and waves and things turning around, and can put distortion in your signal. But a chordal hop over there on the left is where the electromagnetic wave will bounce between the ionospheric layers without hitting the ground. And it's a lot less lossy that way. Also, going off to the lower left is a long path propagation path, which comes up again from the lower right. Now, the long path is a long way around the Earth to the receiving station where you're trying to talk to. And it's good on all HF bands from 160 to 10 meters, and 20 meters is the best band for long path propagation. This is another interesting picture that I thought was very interesting. And if you want to read through this, we're not going to read through it right now, but it shows a very interesting picture of where things are in space. I'm a kind of a space flight nut too. Growing up in the 60s, I really got my interest in radio and how the ground can talk to all the astronauts, and then ended up in '69 to people walking around on the moon. Is all through radio, and I wanted to know how radio worked and get involved in that, and that's where I've been. But I keep track of things in space. The space shuttle flies at 150 to 170 miles. This one is kind of on a low orbit. The northern lights happen in the E region, which is like 90 to 100 miles above the surface of the Earth. Just for interest, the International Space Station flies at 400 kilometers or about 250 miles off the Earth. So it's in a bit higher orbit than a lot of other spacecraft, low Earth satellites, and space junk. Also, you can remember, if you don't know, that GPS, forget that. That's later. That geosynchronous satellites are at 22,000 miles out. So that's way 10 times removed from where International Space Station and the Space Shuttle fly around. So they're way far out with a 24-hour orbit, which makes them the geosynchronous. That's just an interesting side note. But anyway, you can read that later. This one is all about interplanetary physics. You need to understand some about interplanetary physics, the geomagnetic field that surrounds the Earth. You know, the Earth is like a bar magnet, with the North Pole of the Earth coming out the North Pole where Santa Claus lives, and the south end of the magnet coming out Antarctica where the penguins live. So I guess the penguins like the South Pole better, so that's how they settle there. The aurora comes up again in the E layer, and in altitude, let's see, here's my mouse. The E layer is in the very lower reaches of this geomagnetic field, and it's where the lines of flux come out the North Pole up in Canada. Yeah, you got to watch out in Canada because you might see a magnetic line coming up out of the ground just about anywhere.
Don't throw any iron filings in the air, right?
Right, don't throw iron filings in the air, and don't bounce electrons around, because electrons and magnetic fields basically don't like each other. They do strange things to each other, throw each other around, bend and refract and mess around with each other, cause currents to flow. It's a mess. That's where Mr. Maxwell and all his Maxwell's equations describing electromagnetic theory came about, and telling all those interactions between electric fields, electrically charged particles, and magnetic fields, and all the ramifications and the useful things that we've now made from those. So the lines of flux come up, and where the lines of flux start to deviate from each other, which is North and South Pole, is where the aurora happens. Aurora can happen in North and South Poles. You know, on the nighttime side is where you'd see them. During the day, they're too dim to be seen in the sunlight, but they're still there because it's the interaction of all this solar wind. This yellow arrow points toward the sun. Well, I've got a solar flare coming back from the sun, and it's sending all these charged particles to the Earth, and our magnetic field shields the Earth from all this junk coming from the sun. So when you experience a sudden rise in the noise floor across your radio frequency and in all radio frequencies, you can pretty much figure a solar flare is going on and causing extra noise in your receiver. Now, there's some questions in here about the geomagnetic field direction and intensity. It's the parameter is called B sub Z, and we'll go over this in a few minutes about just what that means and how that's measured. But B sub Z gives you an indication of the intensity of these magnetic lines of force out here and their direction. With the lines pointing southward, which means from the North Pole toward the south, are the normal lines of flux from a bar magnet with the North Pole coming out the Canada and the polar regions of the Earth, the North Polar region of the Earth. With the BZ pointing southward, radio conditions are more likely to be disturbed. Radio conditions are disturbed by all this junk coming from the sun. The sun sends out wads of energy, and I'll show you some pages where you can monitor that if you want to get into that. Monitoring the sun and space weather is real interesting stuff to watch and get into. But this is a clue right here. When BZ points southward, radio conditions are more likely to be disturbed. And pointing southward means the lines of flux flow out the North Pole like they would from a bar magnet, a permanent magnet, and flowing into the South Pole. So they're pointing south. Here. NOAA, the National Weather Service, keeps up with space weather besides the weather down here on the ground. And this is one of their websites. They have lots of websites, but this link right here, the swpc.noaa.gov, is a link you can go to. That's where I got this information. This is just one of the first screens that shows the space weather conditions. And when I did this yesterday and took this picture down yesterday, everything is pretty much calm. It's settled. There's no weather disturbances, no geomagnetic disturbances or solar disturbances anticipated, none happening. We get the solar wind speed. I don't know how you would measure that, but they give you a wind speed. It's the flux, the gamma rays, the wads of energy, the wads of magnetic fields that the sun throws out in sunspots. Now, right now we're having very few sunspots, but that's not the point of this picture. Here's the solar wind magnetic field. Here's the B sub T is 4 nanoteslas, and the B sub Z that shows you how the radio conditions will be if it's disturbed is at 1 nanotesla. So that's not real strong. That's very weak. And then here's some noon 10.7 centimeter radio flux. And you'll have to read there. They have a lot of descriptive information, how to interpret these numbers, how to interpret the charts. And the arrow here going to the right shows you that there's, I think I counted, there's 2 more screens of space weather condition material on there. Now here's some information you're going to need to answer some questions. A Class X solar flare. You remember in algebra or taking mathematics that unknown variables were always labeled X, like X-ray? If you remember, the Class X is kind of an unknown. It's described as extremely disruptive. I would call it an unknown intensity. Then you can remember what Class X solar flare intensity relates to. It's extremely disruptive. X for X-ray for Class X. Extremely disruptive. An X3 flare intensity is 50% greater in intensity than the X2 flare intensity. I didn't say that right. X3 flare intensity is 50% greater than an X2. 50% is a number you need to remember. A G5 is an extreme geomagnetic storm level. Right now, these Gs right here, the 24-hour observed maximum and the latest observed, G is none. There are no geomagnetic storms going on right now. The sun is quiet. That's good and that's bad. But a G5, if it came up here as a G5, you're going to have extreme geomagnetic storm levels. 304A refers to 304 angstroms as a wavelength of ultraviolet light. It's like halfway between the highest visible wavelength, shortest visible wavelength we can see, and X-rays. There's also a 3400 or 3000 angstrom wavelength of ultraviolet light, but that's too long, and that's a near ultraviolet. This is a far ultraviolet. This is the ultraviolet light that can cause damage to your skin. And so 304A is an indicator of the solar flux, how much flux, how much ultraviolet light the sun puts out, because when it gets disturbed, it puts out more solar flux. So 304A is correlated to the solar flux index. The wrong way. Okay, now we're going to talk about some practical measurements of radio conditions and what you can expect. This one I use a lot is called the maximum usable frequency, the MUF. Information on it about propagation, real-time propagation. I'll watch this during when I'm working contests. And it's really neat now that I have cell phones, whereas 20 and 30 years ago, I didn't have a cell phone. So sitting out in the field, out in the boonies and field day, all I had were the month-old prediction, well, 2 months old predictions out of QST magazine from the MUF charts. And they were very coarse. They were only given like for every 6 hours, and just a few places across the United States, east, central, and west. So you had to kind of make some estimations. But now I can sit here and I think this updates every 4 minutes, every 5 minutes. And I have my laptop off to the side when I'm running a contest, HF contest, and watching like this is, well, this was, when was this? Yesterday at 2000. It'd be what? So 10 a.m. yesterday I did this. And this is about the highest level frequency that we're going to get for the day. It's kind of hard to read the lines, but what all these lines mean are marked off in megahertz. Right here at the peak out over Hawaii, the MUF is 33 megahertz. But okay, so you can talk all over Hawaiian Islands on 10 meters. Well, big deal. You can't talk to Hawaiian Islands from California or Texas. Maybe in California, you can get up to 15 meters at 21 megahertz. You could talk to Hawaii. From Texas, maybe during the peak yesterday, but advance this a couple of hours and see these lines right here. These are decreasing by megahertz. This thick line right here is the gray line. This is where the sunset's going to come across. Now, you see all these, the megahertz, the lines indicating different megahertz coming across through the gray line. How after the gray line, which is after sunset, they continue to decrease. We're up over Scandinavia. Yesterday it was showing 7 megahertz, so 40 meters would be tough in Scandinavia. They might could work 80 meters in Scandinavia, where these guys over here in Hawaii are chatting all over the Hawaiian Islands on 10 meters. Well, this chart will give you what frequencies you can talk on. The link to this is this one up here, spacew.com, www.realtime.php. And this works fine on your cell phone. If you're out and you want to see where it is. Now, if you're in Africa, things are really messed up. South America can talk to Africa on 10 meters, just across, from Brazil to Western Africa all day long, and all through the evening even. So you can see here what areas of the world can talk to what other areas. Don't expect to talk any higher than 40 meters, and maybe not that up here in Siberia. That kind of stuff you can get from this one. Here's another interesting link that explains this in different words if you're interested in following that. Okay, let's start talking about what happens to electromagnetic waves, which is the radio wave coming out your antenna when it goes through these curved mirrors. This one here on the right, you can imagine a dipole. This line that represents the x-axis. Now time is coming out the z-axis, either time or space. So the z-axis here is distance from your dipole antenna. The red line then will represent the magnetic field. The blue line will represent the electric field as it bounces off your dipole, as it propagates off your dipole. It doesn't bounce, it propagates off of. You're feeding your RF energy at the specific frequency for this piece of wire that's split in two in the middle and with a quarter wave on each end. I mean, that's the first basic antenna I put together, was a dipole. Yet to have experimented with different lengths, I knew what length had to be on each end for 40 meters. So that's what I built, 40 meters, and I had a 40-meter radio that I could listen to lots of CW on a 40-meter radio. Then notice that the electric field and the magnetic field are perpendicular to each other. That's the property of propagating magnetic waves. They propagate off in the z direction, and in a dipole, they propagate equally well off the backside. This is a representation of just going off in one direction. Now, you want to watch, because we're fixing to get these things all messed up, because it's not just electric field in one plane and a magnetic field that's got to be orthogonal to it or perpendicular to it off in the other plane. You see on the left here, we've got some arrows showing how they correlate, the amplitudes correlate with each other. And in free space, it's you've got the peaks of the magnetic field correlating to the peaks of the electric field, and they go through zero at the same time in the same point in space. Now that would be called linear propagation, linear electromagnetic waves propagating through space. Now we start getting these mixed up and tangled up when we start bouncing these off of curved mirrors. You remember that every boundary between ionospheric layers and even between weather system layers and temperature inversions are like mirrors. They're all curved, and weather systems are really messed up. They're not just nice flat curved mirrors. They're curved, they're intertwined on themselves, they've got thunderstorms in them, they've got all kinds of problems. And this lower left is showing your propagation going through a spiral effect, and this is when it's going to become elliptically polarized. This OscarLiang.com was the attribution for these diagrams. I went to the website. It has nothing to do with radio waves of propagation. It looked like drones, a drone store. If you're into drones, I don't know, check it out if you want to see what he's got. But there was nothing about this. That's just the attribution of the diagrams. At the bottom of these pages, I've got the links where on the internet where I got all these diagrams, the ones that I've copied off of, and I didn't want to sit and draw all this. This is really hard to draw. So go look up these links. There's a lot more information at these links, except for that Oscar Liang didn't have anything else at all. I actually looked at it, and there's nothing else there. But all these other pages at the bottom or somewhere on the page, I've got the internet address where these are. A lot of times there's a lot of really good information at those. At your leisure, after you get done passing the extra class exam, for research and general interest. I'm a big research and interest link following person. Sometimes I get into, oops, not that yet. I get into different things that, and one of them caught my virus protection, caught a virus off of one of the pages that caught a virus off one of the pages, and that stopped the computer. And I said, okay, stop, forget that page, delete it. I won't mess with that one. Here, the upper left, we start with the linear polarization. Again, we came off a dipole. You've got the electric field, the magnetic field, orthogonal to each other, set at 90-degree angles to each other. When you start these rotating, there are antennas that will launch circularly polarized radio waves with circular polarization. You can have right-hand polarization and left-hand polarization. And there are some advantages of doing that, but that's not the topic of the discussion today. But those are interesting things to go research and read about. You could look that up in the ARRL antenna book. Yes, I'm a member and I'll give them a plug. It's good information. And so when we start bouncing this linear radio wave off of curved mirrors, we start winding up the fields in different paths. Sometimes it makes extraordinary waves and ordinary waves. We'll get into that question later. But when you start doing this, the propagation path gets messed up, and in elliptical polarization, it's all messed up, it's twisted. The amplitudes of the electric and magnetic field get out of whack. Then you can tear this into different independent waves, the ordinary and the extraordinary waves. Yeah, there it is right there. I knew we were going to get there. Elliptical polarization is a circular polarization where the antenna is not just right and it's got a problem, and the magnetic field or the electric field is stronger than the other. Then you get elliptical polarization. It kind of messes up what you're trying to do with that antenna. But when you get your linear polarization bouncing off these curved mirrors in the ionosphere, they become twisted, they become independent waves. You can have ordinary and extraordinary waves coming off that. Now, one method of modeling ray tracing of propagation paths is the VOA CAP modeling software. And here's their link. It's a tool that amateurs can use. Now, this is something new that I didn't know about. It also said, I read some of the description about it, said that it can give you the MUF information. So I'm going to have to check that out, because this gives you a lot more than just a map of MUF. What's hidden over here is that North America and Texas is where this propagation path starts. This one that comes out right here in the middle of the page. And I put it in Southern Europe. I think it's Monaco is what I picked. I don't know if Monaco has many hams or not. Somebody will have to research that. But there is a clock. This is a
I've worked Monaco. They have hams.
They do, okay. Well, I've not had good enough antennas to do that. So this 24-hour clock right here shows you the muff for all of the, and where it falls in this bands from 80 meters up to 10 meters. And if you look over here at 1500 GMT, whoops, not yet, 1500 GMT, that's when you'll have the highest probability on 17 meters or 15 meters. So, okay, well this, then I don't have to watch the lines of equal propagation flow across the screen and going like, oh dear, it's 2 hours till sunset and the band's going to be shutting down. And I've listened to the bands, watching my muff map, and yes, the band's shut down when it says they do. So, okay, now I'm looking for something new and more exciting than that now. So I found this, and this is one of the questions. Modeling, the VOACAP modeling software models propagation paths around the Earth. Now we get into the troposphere and temperature inversion. You know, the troposphere is where we live. That's where we live, way down here at the bottom of this stack up right here. On the right-hand side is a scale of miles. You know, Denver's at 5 miles. So Denver would be up here at 5 miles. Mount Everest is taller than 5 miles, isn't it? It says 8.5 kilometers. I don't know, whatever, but that's not a question.
Denver's 5,000 feet, which is 1 mile.
Oh, 5,000 feet, that's 1 mile. Sorry, I'm off of my scale. So Denver's still down here at 5,000 feet or 1 mile. So, okay, so Mount Everest can be 5 miles. 5 miles is, what is that, 27,000 feet, I think I remember Mount Everest is. Okay, sorry, I got my scale wrong. But you see, that barely gets up into the troposphere, and the tropopause is between the troposphere and the stratosphere. The stratosphere is where the ozone layer is mainly concentrated. Ozone is charged particles, charged O3 ions. And again, you have charged particles. They do strange things to radio waves. It's a mirror. You see here where the bottom scale toward the left is temperature. We don't do much with pressure. That just shows how the pressure decreases and why on Mount Everest it's hard to breathe. But the temperature here is important because at 6 miles at 30 and 35 and 40,000 feet, where these jetliners fly, and they even fly over these big thunderstorms, it's like 50 and 60 degrees below zero, and that's in C, which is really, really cold. Where the temperature up here around 20 to 25 miles starts warming up, it can warm up to 0 degrees C, or who knows, maybe warmer. I haven't been there, so I don't know. But this is called the temperature inversion, where the temperature starts back away from cold and back warming up again. This is another mirror. Tropospheric propagation of microwaves can be guided along by warm and cold fronts, and you've heard of microwave ducting. That happens a lot over bodies of water. Happens because of temperature inversions. It happens because of this temperature mirror right here in the troposphere up to 5 miles. Then when you get the microwave ducting, that can propagate for 100 to 300 miles, which is maybe what I've got shown by this dark black line down here at the bottom in the bottom left corner. And this is showing how VHF and UHF waves of those wavelengths, 2 meters and 70 centimeters, are going to be curved down just because of the density of the atmosphere. See over here on the pressure curve, the density of the atmosphere is really decreasing up to Mount Everest, and then up to 10 miles, which is what, 52,000 feet? I guess if I got my math, I don't know. That's probably close. 1 mile is 5,000 feet, so 10 miles is 52,000 feet. So that can be off up here, and where the air is very much less dense, but where the air is really decreasing in density, that just the air density change can bend VHF and UHF radio waves. So the guy up here, this was about 2 miles, so that's at 10,000 feet up on the side of a hill, probably in California or up in New England, can have a conversation out here on somebody in the ocean with his boat sinking under this thunderstorm, because the radio waves will bend down. Now the notes here on the right, each change of temperature can be a curved mirror to the radio frequency waves. So changes of temperature, just like changes of ionization, will curve radio waves, make them refract. Refraction is curving. Changes in density of the air bend VHF and UHF line of sight, and that bending extends the radio horizon by about 15%, maybe as much as 20%, but the answer is 15%. So that's about 1/5 to 1/6 of the distance. Well, if this distance across here is 100 miles, that's another 15 or 20 miles you can go out, just because the radio waves are bent. Ground wave propagation is better with vertical antennas at lower frequencies. The vertical antennas are usually used for ground wave propagation, and the lower the frequency, the better off that works. This map is a Hepburn display. It's a display of the tropospheric propagation, and this was a forecast yesterday for today around this time. 1500 UTC is approximately where we are. And it shows off the coast of California these red and real bright orange spots, and off the coast of Baja California. You could do some really good tropospheric propagation with microwaves down here. Maybe even, let's see, I haven't been to Mexico, but the very bottom here at 105 West longitude is the tip of Mexico. I believe that's one of the big Mexican resorts. They could possibly work microwaves up into the southern tip of Baja California, or Baja California work into Los Angeles area, somewhere a path through this orange and yellow zone, according to this Hepburn display. For DX operation, DX meaning making contacts with foreign non-US stations. The newer hams, pardon me, the newer hams in this group may not be familiar with working DX. All the older hams for sure are. When you're working foreign stations in a pileup, you can send your full call sign once or twice. Any more than once or twice just makes the pileup way bigger, and everybody gets frustrated, short-ended, and it accomplishes nothing at all. So your full call sign once or twice in a pileup. DX stations listen on a frequency different from where they're transmitting for many reasons. That's one of those questions where all the choices are correct. A DX QSL manager will handle receiving and sending confirmation cards for the DX station. A DX QSL manager, for instance, would be somebody in Alabama or here in the United States in another state and handle the QSL cards for the D expeditions that are in rare DX places, and other DX stations like Europe or Japan may send them through a QSL manager. And contacts between US stations and non-UX stations are confirmed through the US QSL Bureau. That's USL QSL Bureaus for DX contact confirmation. I think, yes, whoa, somebody's been drawing on my screen. That's cute. I like that. More contest operation notes. VHF and UHF contest activity has the highest level of sideband and CW contacts in the weak signal segment of the band near the calling frequency. I put on here from 3 different places. They're all very good places to look. I recommend the Texas VHF FM Society. They do lots of things for VHF and UHF FM radio here in Texas. And they have all these band plans and point out different frequencies where some of this is FCC mandated. Some of this is just general operating practice. The 144.2 calling frequency is general operating practice. The subband for CW only operation and satellite subbands are FCC rules. And you can look those up, and we'll get into FCC rules next week, I believe it is. I recommend highly icomamerica.com website. Here's the link to a bunch of amateur tools they have. They have a lot of nice charts. If you haven't seen their charts, they're very nice. They're very well done, very professionally put together. Besides, I like their radios. I don't have any financial interest in ICOM America. I don't even own stock. I don't know if they have stock. I don't play stock markets anyway. Whoops, what happened? There, back. But their website for amateur tools and charts, and nowadays you can download these to your computer, look at them on your computer, print them. If you have a high definition printer, they print very nicely. This is a section taken from the 2-meter line, and they have, they've got this list of all the amateur frequencies available and allocated to amateur radio operation in the United States for every band that hams can operate on. So that's a useful tool to have around and refer to if you don't already have one like that. I believe there might be something similar in the Gordon West book. Now the different colors I maybe have deciphered correctly, but if there's one of them wrong, then you can blame my defective eyes, because some of the colors don't register just right to me. But the deal is that right here in the middle of the weak signal band is the calling frequency 144.2, and that's where sideband and CW contacts are going to be found during contest activities. This is calling frequency at .2. Then there's a satellite subband, and then you get into the FM repeater bands. And between FM repeaters, you can do FM simplex and some digital operation. ARRL, which I highly recommend, also has a band plan, and they show band plans for broken out in this type of detail for every HF through UHF band. And on 6 meters, the calling frequency is 50.125. Contest rules usually exclude 30 meters from contest operation. That's every contest set of rules I've read does exclude 30 meters on HF. Cabrillo format is the standard for submission of the electronic contest log. When you're done, you get your logs from whatever software, and there's web pages, and they tell you in the contest rules what web page you can use to put your handwritten logs in Cabrillo format and get those submitted for the contest that you worked. In contest, it's not a good idea, and it's usually prohibited by contest rules to do self-spotting. Self-spotting is where you post your own call sign and frequency on the spotting network or bulletin board so other people can come work you. That might be useful to make rare contacts like EME contacts, sporadic E, or meteor shower contacts, but self-spotting during a contest is usually prohibited. And I think that's it. Let's see, I need to unshare. We'll stop sharing that. And I have another thing I want to share, and we'll go down through the questions in this. Now I just had those open. Where'd they go? So I haven't been monitoring the chat window. I don't know if there's questions. John, have you seen any?
It helps if I unmute before I try to talk.
Such as live radio.
Yeah. There was a comment that 260 miles is 3.25% of the Earth's diameter. So
that's right. Yes.
That demonstrates what you were talking about.
Yes. The ionosphere is a very thin layer surrounding the Earth. Our atmosphere is even thinner. It's not even as thick as the peel on an apple. So yes, you're correct. It's a very small slice. Let's see, I'm looking for a Word document. The Word document is open, so I should be able to share it. And if I go to show all windows, I guess my computer had a hiccup, sorry. Skywaves and Contesting, a Word document. That should be this one. No, I don't want to open it. Am I sharing?
Yes.
You see that? Okay, let me make it bigger. No, come on. We'll make it bigger yet. There,
Press,
even better.
Press Control Home.
Okay.
That's your top of the document.
All right, here's the first one. All right, for those of you that have a book, we're on page 43. These questions in this list, like John has organized and arranged in the same order as the questions are in the book. We'll go down through the question list. For those lacking a book today, we'll go through the questions on the screen, although you will miss some of the diagrams in the book. Some are similar to what I've had. Some are in addition to, which are very useful. And I recommend you go through the book, and when you get your book, to go read all the explanations about it. Now, I prefer not to give you all the incorrect information for a question. I want you to know what the question means and is answered. We talked about extraordinary and ordinary waves as they bounce off the ionosphere. That's independent waves created when the electromagnetic waves become elliptically polarized. The key here is elliptical polarization. Let's see if I can highlight this on the fly. Does that work? You see a highlight on elliptical?
You got it.
All right, because none of the other answers have elliptically polarized, but that's what makes extraordinary and ordinary. Okay, so we'll keep going. Let's see, what happens to linearly polarized waves that split into ordinary and extraordinary waves? They have become elliptically polarized. There's that answer again. Okay, so now everybody knows about bounce it off polarization and ionospheric layers. Elliptical polarization. What is meant by circularly polarized electromagnetic waves? That's where the electric field rotates. You remember one of those pictures? I'm not going to try and bounce around. I'm not going to try and bounce around between screens because I seem to get lost doing that. Fact number one, I don't like PowerPoint. So we'll go with this. But I do like PowerPoint's presentation of pictures and what I can do with that and diagrams and stuff. I used that in the past at work and can put those together. They're very informative, but it has its limitations when you're switching between these screens to share. So circular polarization, the electric field is rotating. What does the VOA cap software model? What were we showing with VOA cap software? It's HF propagation. That's what we're talking about with VOA cap software. What does the radio communication term ray tracing describe? What are we doing when we ray trace? We're looking at the radio waves path through the ionosphere. So you got the ionosphere, right? Which of the following amateur bands most frequently provide long path propagation? Which was the one most frequent? That would be 20-meter band. Okay, like that. What about amateur bands that support long path propagation? Pretty much all the HF bands can go long path when the ionosphere is lined up correctly and there's not too much noise on the bands. What might help restore contact when DX signals become too weak to copy across an entire HF band a few hours after sunset? What happened a few hours after sunset? The higher frequencies started disappearing. So you have to switch to a lower frequency on the HF band.
Another way of saying it is the maximum usable frequency drops.
Yes, that's what you've experienced, a drop in the muff. However, that's not what the question. I think one of the previous.
Well, that's why the answer is you move to a lower band, because the maximum usable frequency is not as high.
Right, that's right. I think one of the previous classes had discussion about muff. Is why that picture still in his book and how I got latched on that. That was way back. Why is chordal hop propagation desirable? Remember chordal hop, how that worked? That was bouncing through the ionosphere between ionospheric layers, not using the Earth as a reflector because the Earth is lossy. There's less loss when you stay up in between layers in the ionosphere than when you have to bounce it off the Earth. That was chordal. Chordal is a mathematical term that talks about going around the outside of a circle. And in this case, we're going around the outside of the Earth. So what's the primary characteristic of chordal hop propagation? This is the successive ionospheric refractions without reflecting from the ground. Reflecting is where it bounces off something. Refracting is where it bends. A refraction is a bending in the ionosphere. Transequatorial propagation is between two mid-latitude points, north and south of the equator. It's on opposite sides of the equator, in the north and south of the equator. I didn't highlight that, did I? There. What's the approximate maximum range for using transequatorial propagation? That would be 5,000 miles. I guess somebody decided that, or there's proof. Don't know. I've never lived.
I'm sure that it's mathematical.
Okay.
And a typical hop across North America on 20 meters is going to be about 1,500 to 1,800 miles.
Uh-huh.
Maine to Texas, Texas to Oregon. So the transequatorial propagation is quite a bit greater distance, and it's because of the curvature in the ionosphere.
Yes. What's the best time of day for transequatorial propagation? Be in the afternoon, right after the sun passes the maximum. What might be indicated by a sudden rise in radio background noise across a large portion of HF? You've had a solar flare, noise coming from the sun. Solar flare can cause the rise in background propagation. What's indicated by a rising A or K index? I don't remember us talking about that one. Maybe I skipped that part. A or K indices are increasing. Where did that comment go? I know I put that on the chart. Oh, well, it was hidden anyway. Somehow it got lost. I'm sorry. A and K indices indicate disruption of the geomagnetic field. Disruption. It's increasing disruption by when they rise. A and K indices show the magnitude of the disruption of geomagnetic fields. So when they rise, we highlight rising too, because that's part of the key to this question. See, now on the test, you remember, well, you haven't, not everybody's got their book. There's a few pages in the book, and you need to read this pretty careful about how the testing works. For those of you that have just taken the test, you may already know this, but on the test, the test can be made up where these answers are in any order. This geomagnetic field increasing may be answer D on the test. You just don't know. So you have to know that rising A and K indices are increasing the disruption of the geomagnetic field. And so you need to understand the key words. When you get your book, go through the questions, highlight, get you a yellow highlight marker or whatever other color highlighter that you like, that you can see well, and go through there. Some of the pinks and greens, okay, they're highlighters. They call them highlighters, but they don't do much for me. I like the yellow one. And go through your book like this and connect the words that connect. Rising A and K is increasing disruption of geomagnetics. Okay, we got that out of the way. Which of the following signal path is most likely to experience a level of absorption when A and K index is elevated? Well, A and K index elevated is rising disturbance in the geomagnetic field. Where did the geomagnetic field most reach the ground closest? At the polar regions. So the polar region signal path is going to be more upset when A and K is elevated. That's the A and K index is all about geomagnetic fields. What does the value of B sub Z represent? Remember, B sub Z was the intensity of the interplanetary magnetic field. So it's direction and strength of the interplanetary magnetic field. If I can get my mouse to work better. So that was the B sub Z, direction and strength of the interplanetary magnetic field. About B sub Z again, what orientation increases the likelihood that incoming particles from the sun will cause a disturbance? Orientation, the southward orientation. Come on. You know, my mouth is getting ready for lunch, I guess. It's getting close to time. Yeah, we've got time, I think. We'll go over it. Okay, that's B sub Z, is southward orientation is most likely to be disturbed. Which of the following descriptors indicate the greatest solar flare intensity? The greatest solar flare intensity, you remember, was extreme, unknown, X. That's your class X. Hello. Highlight. Thank you. How does the intensity of an X3 flare compare to an X2 flare? How much greater? He's 50%. X3 is 50% greater. What does the space term G5 mean? Well, G is for geomagnetic. So what number of geomagnetic storm would be extreme? That's the G5. What does the 304A solar parameter measure? Solar parameter is going to be indicating UV emissions at 304 angstroms, which is correlated to the solar flux index. What time of day can sporadic E occur? Anytime. It's sporadic, so it's anytime. What time of year is sporadic E propagation most likely to occur? Around the solstice, especially during the summer. It's most likely to happen during the summer. When a meteor strikes the Earth's atmosphere, oh, here's our meteor shower question. Cylindrical region of free electrons is in what layer? It's in the E layer for meteor. I like that one because this came up, I think it's even in the technician class license, that everybody laughed when I made that.
That's a neat thing. What I realize is that the E layer is far enough down that when a meteor strikes the atmosphere, it's at that altitude that the meteor burns up in that 60 to 90 miles. Above that, the atmosphere is not dense enough to do that.
Right, that's right. It's not dense enough. A lot of other interesting things happen to especially the solar wind as it comes off the sun in the E layer. You'll have to read about that. That's not part of the test. Which of the following frequency ranges is most suited for meteor scatter? 10 meters to 2 meters. Everybody knows what frequencies those are, right? 28 to 148 megahertz. That's where that chart from ICOM will help you. The chart from ICOM shows you frequency and it shows you wavelength, so you can get those two synonymous in your brain. So somebody switches, hams I've talked to will switch between meters in wavelength or centimeters and frequency just routinely through conversation. So you've got to keep track of knowing what frequency goes with what wavelength. So this is 10 meters to 2 meters. Which of the following digital modes is designed for meteor scatter communications? It's the MSK 144. You can Google that and read more about it. Let's see, what page are we on? It might be some explanation about it in Gordon West's book. Meteor scatter, MSK 144. He doesn't tell you much about the modulation, but it's very interesting to read. Well, I'm
Well,
interested.
it's one of the James Taylor package in the WSJT -X family, and it's designed to repeat the data very quickly a number of times in each transmission, so works.
Okay. What's a good technique for making meteor scatter contacts? Well, it works on 15-second time transmissions. Some of them do. MSK 144 is faster than that. Use a special digital mode, that's MSK 144. Short transmissions, repeated call signs, and signal reports. So all these choices are good for meteor scatter contacts. Thought there was another one about meteor scatter, that's somewhere else. Oh, that's for aurora. We'll get to it in a minute. What's the cause of auroral activity? That would be the E layer with charged particles from the sun. That's the solar wind, and Earth's magnetic field. So that's another interesting thing that happens in the E layer is the aurora. Which of these emission modes is best for aurora propagation? UCW, and usually very fast CW that takes a machine to copy it. But that's for aurora, UCW. Why does the radial path horizon existence exceed the geometric horizon? Page 55 in the book, if you're following along. But the radial path horizon can exceed it because of the downward bending due to the density variations in the atmosphere. Now, in your book, if you've got your book and looking at it, there's a nomograph that talks about antenna height, effective radiated power, and range. And I really believe that chart's wrong. The range, I believe, should be multiplied by 10 miles. So instead of going 2 miles on 5 watts, you can go 20 miles if your antenna's high enough, because I can work. My house is about 25 miles from downtown Dallas repeaters. And if I put my antenna up about 25 feet, that antenna's line of sight to downtown Dallas with a little bit of help from the downward bending. And I can work line of sight on 1 watt, 25 miles with the help of this downward bending. But that's not what his chart says. His chart says 2 miles. So I've got a problem with his chart. But that's not the first problem I've got with Gordon West's book. So anyway, I'm making a list of those. By how much does that distance exceed the geometric horizon? Geometric is line of sight, which is where light is. And it can go 15% more. Not twice, not 4 times, 15%. It's just a little bit more. Tropospheric propagation of microwave signals often occurs in association with C, warm and cold fronts. So we didn't talk about the warm and cold fronts in the troposphere. Troposphere is where all the weather is. Warm and cold fronts can guide microwave signals along. So you'll have to watch for that if you get up into UHF. UHF radio is good for that. Atmospheric ducts capable of propagating microwave signals over what geographic feature? Atmospheric ducts can propagate microwave signals. And UHF is at 0.5 gigahertz, so it's close to microwave. Over what geographic feature? It can go great over bodies of water through an atmospheric duct. Microwave likes to go over bodies of water. What type of atmospheric structure can create a path for microwave propagation? It's like a mirror for microwaves, temperature inversions. And what happens, where was that one? The warm and cold fronts. What happens at warm and cold fronts? They're temperature variations. They're just moving along. They're not vertical, they're horizontal temperature variations. So microwaves can propagate horizontally across.
There's also in the weather thing, there's also an ionization because of the wind currents as the two fronts meet, two bodies of air.
And I suspect that ionization is part of the mirror activity going on. Oh, and that ionization is also what sets up lightning. So that's a whole nother topic, is how lightning gets set up along thunderstorms and things and cold fronts. But we won't talk about lightning today. What's the typical range for tropospheric propagation of microwaves? It can be 100 to 300 miles. Can reach quite a ways, but not across the United States. Halfway across Texas.
Yeah, Wayne, I'm going to interrupt you for a second. We're just past noon. You have 11 more questions to deal with. I think we will go ahead and do those 11 questions and then break, if that's acceptable. If you need to break away, feel free to do that. But I'm sure there's some in this group who are clock watchers like me, and I want to give you official permission to do the last 11 questions. Go ahead.
Okay. Thanks, John. Yes, the 11 questions may be about 5 minutes. Hepburn maps are predicting tropospheric propagation, is what they're going to be predicting. How does the maximum range of a ground-based propagation change, ground wave propagation change, when the signal frequency is increased? It's going to decrease, because ground wave propagation is better with lower frequencies. So if you increase the frequency, it's going to get worse. What type of polarization is best for ground wave propagation? That's the vertical. Because most of the public service and police cars back when they were using VHF and frequencies around 10 meters, 10 to 6 meters would all have vertical antennas. So it's vertical. How should you identify your station when attempting to contact a DX station during a contest or in a pileup? Send your full call sign once or twice. What might a DX station state they're listing on another frequency? Many reasons. They can get away from some of the responding stations. They can reduce the QRM they're hearing to separate the calling stations from the DX station, to improve operating efficiency by reducing interference. And in this case, all these choices are correct for DX stations listing on another frequency. Cabrillo format is the standard submission of electronic contest logs, is the format for submitting contest logs. Self-spotting, that's where you post your own call sign and frequency on a spotting network. And most contest rules prohibit that. During a VHF and UHF contest, which band segment would you expect to find highest level of sideband and CW? That would be in the weak signal segment by the calling frequency. So start out the calling frequency, and as pileups happen and the frequency gets busy, move away slightly. You start at the calling frequency. Which of the following bands is amateur radio contesting generally excluded? Don't do contest on 30 meters. Let's see, no contest on 30 meters.
Yeah, I want to add to that. The bands 60 meters, 30 meters, 17 meters, and 24 meters were added after the World Administrative Radio Conference in the 80s. And we share those bands, so they're not as open to contesting. If you've ever been in a contest or been trying to do a net or a schedule during a contest on the bands where the contest is going on, you can be very frustrated in not being able to get there. And this particular question just identifies one of those bands. Go ahead.
Right. Yes, out of this list, which is excluded, but it didn't list the others that you mentioned, which, yes, those are also excluded. What's the function of a DX-QSL manager? He manages sending and receiving confirmation cards for a DX station. Sending and receiving the cards for DX. Which of the following contacts may be confirmed through the US QSL Bureau system? That would be the contacts between the US and non-US station. It's for DX contacts. Oh, that's it. So we did it in 5 minutes. But that's a review of the questions in the chapter in this book. Go over them. Circle the right answers. Make sure you have the right answers attached to the keywords in the questions. This is what to look for in the questions. That's all. This has been K5GD.
Okay. Before we all disappear, we will reconvene at 1 o'clock.